Good afternoon, judges. My name is Kulsoom Syed, and I'm studying Masters in Artificial Intelligence and Machine Learning. And yesterday and today, we have seen some amazing projects and some really interesting insights about generative AI, transformers, and convolutional neural networks. So my project is focused on image captioning, which is a part of generative AI. So it is basically generating a textual description of an image. So it's like having a model look at a picture and then it tell you what it sees. So if I give this picture to a proper standard state-of-the-art model, it should generate a caption like this: a large modern building with extensive parking lots, blah, blah, blah. But when it comes to chest X-rays and medicine domain, this is a bit more trickier to do because the images in, like, for example, chest X-rays actually look very similar, and a vision medical captioning model cannot differentiate properly between these two images. And it might generate a caption that actually is very similar. And because our normal pre-trained medical image captioning models are actually pre-trained on data sets like ImageNet, it won't work well on chest X-rays. So why are we doing this at all, right? Because image captioning models can be faster than a medical expert. However, a radiologist can understand the full context of the patient, like their medical history, but a captioning model won't be able to, a visual captioning model won't be able to do that. A captioning model is also not susceptible to fatigue, and it's also available 24/7, allowing continuous real-time diagnosis. However, a medical expert can handle complex and rare medical conditions better, because in medicine, it's harder to get data sets for rare medical conditions. My project attempts to understand the full clinical context of the patient, and so we can also handle the complex and rare medical conditions without using a lot of data. So the data set I'm using is a mimic chest X-ray data set. I'm using the JPG data set instead of the DICOM because it has 377,000 images. However, I'm only using 4,057 images with a single disease. So I'm doing this just to simplify my process a little bit. And from this data set, I am taking the image, its medical reports, which I will be referring to as a true caption, and the label of the image. And before I start my process, I first clean the medical report to remove all the artifacts and white spaces, and I feed this caption into my model. So the first two models I make are ResNet 50 with GPT-2, and the second model I made was with Vision Transformer and GPT-2. The reason I used ResNet 50 because it is well established, and VIT is also, the Vision Transformer is also very recent. And first I will train the feature extractor on my training set, and then I will feed that embedding space into the GPT-2 model, which is fine-tuned on medical reports. So when I feed the test image into the feature extractor, it will place this test image into the embedding space that will then be fed into the GPT-2, and I have made a small tweak in the GPT-2 which uses a starting word to generate the caption. So I'm using a disease label as a starting word to generate my caption in hopes that it will generate a caption that is more contextual. However, we can improve this slightly by using self-supervised contrastive learning. So this is a type of contrastive learning where you have an anchor image and it is augmented, rotated, rescaled, recolored, and a similar pair of that image is made. So once that image pair is created, we push the image and its augmented pair closer together in the embedding space, and all the other pairs, the anchor image and all the other features, are pushed further apart in the embedding space. So this is the similar thing that I've done with chest X-rays. I have taken a chest X-ray and its augmented images, and then I have pulled them closer in space, and the negative pairs I've pushed them further apart in space, and then I have generated caption using the same, and I have developed two more models based on that. However, there is another type of contrastive learning called supervised contrastive learning. This uses the labels of the images as well. So there is an anchor image which has a label, and another image that may have the same label but might look different. These images are pulled together closer in space even though they might look different, and all the other images with a different label are pushed further apart. This is the same analogy I'm using in my models as well. So there are two types of supervised contrastive learning, and I have used them to create 4 more models. So the chest X-rays with the same label are pushed closer together in space. And then I have made another model which does not use the disease label as the starting word, because I didn't want to assume that using the disease label as the starting word would generate a better caption. And then I have actually used contrastive learning on the GPT-2 to fine-tune the GPT-2 on medical reports as well as the images with the same labels. And then I have fine-tuned GPT-2, and then I have combined the losses to train the model again. And this, there's not any drastic difference between the models, except the last model that I created actually gave me really better results on BERT score, which calculates the cosine similarity. And another score I'm using is WMD, which is the word movers distance. It calculates the distance between the reference caption and the generated caption, and the smallest distance is actually, it means that the model has performed well. And this is the generated captions that I got from all my 11 models. Not sure if you can see it, but my captions were able to find certain diseases almost exactly the way that the true caption, the true medical report was able to, had listed. However, it's also listing certain diseases that were not present in the true medical report. So I'm not a medical expert, but I am hoping that with collaboration with a medical expert or radiologist, I can figure out if my models are performing the way that it's intended. So I actually performed this because I want the medical expert and the captioning model to work together in situations where there's triage required in emergency room, routine diagnosis, second opinions, and medical research. Like the captions can be used further for more research, like object detection. And there's a lot of improvements and considerations to be made, because this is I made these series of experiments over the last 2-3 months, and I worked with a very small data set with only one where the images had only one disease. So with more data, that is under 377,000 images, we can effectively perform retraining. So I was working with pre-trained models, but if we retrain from scratch and rewrite all the model weights, then we might be able to perform, we get much better results. And if we use DICOM checks X-ray images, they will have a better feature extraction results. We can also use models like VILTs to get a shared embedding space where the visual features and the textual features can be aligned together. And this might actually remove the need for contrastive learning. And we can also use GPT-3 and 4 instead of GPT-2 because of my computational restrictions. I use GPT-2. And we can also use this to generate a complete report from scratch. I actually restricted my captions to only generate captions that were less than 50 characters, but we can remove this restriction. And interpretability of the embedding space is also a necessary area in generative AI. And comparison with other state-of-the-art Gen AI models. This is because developing an effective strategy to evaluate generative AI outputs is something that needs to be studied. And the thing is that most of the papers are using different data sets with different subsets, and the outputs that they get are very different from each other. So it's hard to compare, which is why I decided to make 11 different models and compare them within each other. So this is also an interesting area to look at. Thank you.